Recording. That's loud. Okay. All right. So today we're going to be spending some time talking about circuit fundamentals. Some of this will be review for you if you did 16A when it had circuits, or 16B, or maybe you did like physics C, E, and M in high school. Some of it'll be review, but then I'm hoping to extend the topic into how does this actually apply to what happens when you're designing a circuit board, and what sort of effects do you see on a real printed circuit board. So, what topics are we going to be talking about? Like Ohm's law, KVL, KCL. That's going to be the first thing. If you don't know what those mean, we'll go through it in a second. Then we're going to be talking about the main three circuit components, which are resistors, capacitors, and inductors. What are those? How are they created? And what do they do? And then, and how they're used in real circuits. And then we're going to go through some more miscellaneous circuit design considerations, just general things that I didn't know where to fit in a different lecture, like polygon pores on your PCB, trace widths for power versus signal, decoupling capacitor, a bunch of things that I haven't listed. So this is just sort of a odds and ends filled lecture. And I thought this t-shirt would be funny. So I actually feel like I know too much about circuits now, because I was looking at a lot of these t-shirts before this presentation. I'm like, but wait, that's just this circuit. Like this one is actually not a functional circuit. So this one, what, you don't understand? All right. Enough about that. Let's yeah, Nathan. Oh yeah, I can if you can just go to Eek's course slides in the Google Drive, that's probably easiest right now. But yeah, sorry, I'll make sure to send the links beforehand, but you guys have access to them all in that folder. This is the circuit design fundamentals slideshow link. All right, so first are resistors. Resistors basically just make it harder for current to flow through your circuit. Yeah, I don't know how to explain much more than that. Resistance in your circuit will sum as you add more in series. So if I ran through something that was difficult to go through, and then I went through another thing that was difficult to go through, I'm just going to have to go through more difficult things, right? But if you put them in parallel, they actually sum in this funky way. Also, by the way, this isn't exactly a theory lecture, so I'll give you guys some like rule of thumb equations, but I'm not going to go through how to derive that, but you will in 16B. So if you put them in parallel, they sum like that, and basically that means that the total resistance that you see is going to be less than any singular path, because you can go through all of them equally. So if we had like two 4-ohm resistors in parallel, that would actually be, it would look like a 2-ohm resistor, because you can go through both paths. They come in many different form factors, so I just put a photo of a lot of them on here. A lot of the stuff that I'm saying, you're gonna hear once, and then you're gonna keep hearing it for like the next like 4 years as you go through school. Resistors, you're gonna see a bunch of different form factors, like through hole, which is what a lot of these ones on the top are. It's like a wire, and it goes through a hole in your PCB. Or SMD, which is surface mount device. Sometimes you see SMT, surface mount technology. They refer to generally the same thing. Then there's other things like potentiometers, which is where you can see there's one on like the far right on the bottom. And that's like a resistor with a swiper in the middle. So you can change where the middle sensing point of that resistor is. So it's usually like, sometimes it's a bar or like a round circle, and you can change how much of the resistance you see based on, like, if the wiper is in the middle, there's going to be equal resistors on both sides, versus if I was connected over here, this one's going to be like a third, and this one's going to be 2/3 of the total resistance. And so you can use that for knobs. And they have many different purposes. Mostly resistors can dissipate power or drop a voltage across them. And then others of them have special purposes, like they can sense temperature. When you have a thermistor, that's a resistor that's changing its resistance based on the temperature it's existing in. We can also use them to filter signals, which we'll be going through in a couple of slides. But yeah, generally, does anybody have a question? Like, is anybody confused on like what a resistor is, like what the general idea we're trying to get out of this? Because this is like building block number one for circuit design. Okay. Um, all right, so now a little bit about like how do we use this? So Ohm's law, that's Mr. Ohm right there. Is voltage is equal to current times resistance. And a good way to think about it is Ohm's law triangle is that little drawing up there, like on the middle right. And you can use that to basically think, so you see the triangle. So V is equal to I times R because they're on the same level. But then if I want to know current, that's equal to V divided by R because they're on top of each other. Or if you want to know resistance, that's equal to V divided by I because they're on top of each other. So that's just a little mnemonic device so that you never forget Ohm's law. You can always think, okay, which part of the triangle do I want to know? Okay, are the other two parts of the triangle above each other or next to each other? And so with Ohm's law, we get basically the two most useful ideologies and equations in circuit design. We have KVL, which is Kirchhoff's voltage law. I should have written out these acronyms, but basically it's just the idea that if you go around in a loop, the sum of the voltages in that component are zero. And what that relies on is if I start at a node or like a wire, and I end at that wire, I have to be the same voltage, right? Because that's where I started and I ended, and the wire can only have one voltage on it. So the sum of things around that loop must be zero. All right. And then KCL is Kirchhoff's current law. So the sum of currents entering a node must equal the sum of currents exiting the node. Once again, if you think about some point in the circuit, you need conservation of charge. You can't have current going into this and like disappearing into nothingness. So current in must equal current out. And so now I have a little problem here for us to work through. So can anybody, based on what we just learned about capacitors in parallel and capacitors in, or not capacitors, resistors in parallel and resistors in series, let's figure out what the current out of this voltage source is. And then let's also figure out what the voltage is on like that top right node based on like what we just learned. So does anybody have recommendations on like what we should do first to get there? Yeah, Amy. Sorry, could you speak up? Sorry, could you speak up a bit more? For which two? Or for all three or? Uh-huh. Yeah, so find the parallel resistance between RA and R4. Okay, and you're saying that's 2 ohms? Okay, yeah, that's good. All right, so because one nice thing to know is because we don't need to figure out the current between each path, I could ask you guys what's the current between each path, but once again, that'll be the same, right? Because they're the same resistance. So we can sum those two in parallel. So now we have like an 8-volt voltage source and then a 2 ohm resistor and a 2 ohm resistor. So if we wanted to tell, I guess let's do the current first. Like what's the current through this loop? If we have like a 2 ohm resistor and a 2 ohm resistor, what's the next thing we could do?
Side. Well, current is equal to voltage divided by resistance.
Exactly.
So 8 divided by 4.
Right, because the resistors are in series, so we'll sum it becomes 4. Then voltage divided by resistance equals current. So it's going to be 2 amps, right? All right, that's very good. Now, there's two other ways to find the voltage. So now we know the current. It's 2 amps to the 2 amps coming out of the voltage source. Now we want to know the voltage on the top right corner. There's sort of two ways we could do that. We could take the current that we just figured out, and we know that however much current times the top resistance will drop from our 8-volt source. Or we could also, like if we had never figured out the current, we can use the voltage divider equation, which I'm not going to derive here, but the voltage divider is basically if you had a voltage source or a voltage input and then resistor on the top and assume the two parallel resistors are one, you can say the voltage at the top right node is going to be the vertical resistor divided by the sum of the resistances times the input. Or like I said, we can just use the current. So we know that 2 amps to that top resistor times the 2 ohms is going to be 4 volts. And so there will be a 4-volt drop across that. So 8 minus 4, we'll have 4 volts at the other side, right? And that makes sense too, because it's a 2 ohm resistor and a 2 ohm resistor. So if we had 2 ohms over 2 ohms plus 2 ohms, that's 1/2. So it'll be half the voltage there. All right. Does anybody have questions? Or also, this lecture is like pretty sparse. So if anybody just wants to like dive into like something specific about any of the figures, we have time to do that. All right. Hopefully this stuff is all making sense. Like this is like we're just starting off at ground floor. All right, capacitors, next most important circuit component. Capacitors are basically two metal plates that are on top of each other, and they store energy through an electric field between the two plates. So if you guys have done physics E&M, like either before Berkeley or if you've done physics 7B or 5B once you've gone here, you've probably gone through this already. The most important equations to know for capacitors are that the charge on the capacitor, Q, is equal to its capacitance times the voltage on the capacitor. And from that, if we take the derivative on both sides, you can actually get dq dt is equal to capacitance times the change in voltage. And dq dt is just the definition of current. So that's another good equation if you guys need is the current, and then if you divide over the capacitance, current divided by capacitance is equal to the change in voltage. So if you guys are running a current through a capacitor, you can tell how much the voltage changed. And so like I said on the resistor slide, but it should hopefully make more sense now, impedance. Impedance is like when you're looking in the frequency domain. So I don't know if they cover this in 16A still, but just a quick preview. We look at circuits in like the time domain, which is like what is happening in real life. But then we can also look at things in the frequency domain, which is instead of your bottom axis usually being time, it's frequency. So what happens to different frequency signals as we put it through the circuit? So the impedance in the frequency domain of a capacitor is 1 divided by j omega c. And basically what that means is j is like the imaginary number. So we use j in circuits because I is already current. So if you ever see j, that's what it is. And then omega is the frequency of that signal, and then capacitance will be your capacitance. So as the frequency increases, our denominator is getting larger, right? So our impedance is going to decrease. So what that means is as the frequency of your signal increases, your capacitor is going to look more and more like a short circuit. So if we have really high frequency signals, it's just going to go through the capacitor. It's not going to like charge that capacitor or really affect it in any way. It's just going to like be like a short circuit. It'll go right through it. And so how you sum them, it's actually it's the opposite of resistors. So capacitors in parallel will sum because if you think like if you draw out the circuit of two capacitors in parallel, imagine you slowly push those circuit components more and more together, and the nodes at the top and bottom come more and more together, right? It looks like the bottom plate of each capacitor is shorted and the top plate of each capacitor is shorted. So it's looks like one capacitor, right? That's not the exact math, but it's like a graphical way to think of why capacitors in parallel should sum. And then capacitors in series actually do the opposite, where it's the reciprocal sum is the reciprocal equivalent. And then this photo is just some various capacitors you can see. The ones on the bottom left are MLCCs, which is multi-layer ceramic capacitors. It's basically modern chip capacitors. It's like a bunch of layers of metal with dielectric between them, and they print it similar-ish to how circuit boards are printed. It's basically a lot of layers. And then it's a ceramic dielectric. Then you have the ones on the top that are in the black casing. Those are usually more specialized capacitors. They're usually polarized, like tantalum capacitors. If you look those up, they usually come in those packages. Although we try to stay away from tantalum capacitors because they're made from conflict materials. So yeah, we try not to support that. And then you have some through-hole capacitors like that. Sometimes through-hole capacitors look like these blue ones on the top. Sometimes they look like these beige ones on the bottom. Those are like ceramic through-holes. But then sometimes they look like this black cylinder over here, and that's electrolytic capacitor. So that one actually has like a fluid inside of it that helps with the dielectric. And just something important to know about those ones, they have etched lines in the top so that if you overvolt them, they will like blow out of the top and like projectile. So make sure you don't overvolt those ones, and also like just be careful of them when you're working with them if you aren't sure of your voltages, which you should be sure of your voltages beforehand. But just to keep in mind, these are usually power components a lot of times, so they can blow sometimes. All right, so now we know resistors and capacitors. What's like one of the most interesting things we can do with that? Now we can make filters. Filters are very nice. So if we make this circuit right here called an RC filter, this is what's called a low pass filter. So it'll allow low frequency signals to go through, and all high frequency signals will like not be able to go through. Does anybody have any intuition as to like why do you think low frequency would be able to go through and high frequency wouldn't, based on like what we've learned about a capacitor? Yeah.
It's like, 'cause it kind of like cushions out, so like at like really high frequencies, it kind of like, I don't know how to say it, but I feel like it absorbs it.
Yeah, so that's true. In transient events, a lot of times capacitors will just absorb charge and then slowly redistribute it later, that is a correct way of looking at it. We can also look at it as the capacitor impedance decreases as frequency increases. So those signals will actually be shorted to ground, because if the capacitor impedance is much lower, like if we did a really high frequency signal, it's just shorted to ground. So that voltage will be zero. But for low frequency signals, if you think about it in the graphical way, as we charge this capacitor, that capacitor is going to have some voltage across it. And so that basically just looks like RC charging, which I realize is something that I don't explain in this lecture. So you guys might be confused, but we can go over RC charging waveforms at the end because those are important to know as well. But just some general numbers for this. You can see the frequency response here. I just wanted to use this to show that at some cutoff frequency, the signal is going to start getting attenuated. It goes down, and these are log plots. And that frequency at which the cutoff is 1 over 2 pi RC. So that's just a good number to know. And it's important to know at the cutoff frequency, you already have some attenuation. You have -3 dB, which is equal to 1 over square root of 2. So a use case for this would be like you have an analog sensor and we want to get like the high frequency noise off that analog sensor. So we do this on the pedal sensors, because the pedal sensor should not be like changing like really high frequency. So we want to filter all of those so that it's, because we know that's noise, like the pedal's not changing that quickly. So we put this onto the pedal sensor so that only very low frequency or DC signals can pass. And that basically helps the microcontroller read a cleaner signal. Okay, and the opposite, CR filters. This is a high pass filter, right? So as the frequency increases, the capacitor is going to look like a short, so it's just going to go right through. But at low frequencies, the capacitor is like a block, so nothing's going to go through. So a lot of times a capacitor set up like this is called an AC coupling capacitor, because you could basically just have two circuits, put the capacitor in the middle, and only AC signals are going to go through because you have to have some frequency to be able to go through that capacitor. And the frequency response basically looks like the opposite. You're going to get less attenuation once you're going to get no attenuation once you're past the cutoff. But before the cutoff, you're going to have that slope. And the cutoff is still 1 over 2 pi RC. Any questions on filters? Filters are also an entire field that like you could get a PhD in. So you could spend your entire life focusing on these if you'd want. I'm barely scratching the surface. All right. Our third circuit component, final one, inductors. Inductors are basically coils of wire that store energy in a magnetic field, right? So we have electric field, magnetic fields, capacitors store energy in electric fields, inductors store energy in magnetic fields. And the impedance of an inductor is J omega L. We use L to measure in inductance. And so as frequency increases, the impedance of your inductor is going to increase. So you can think that like low frequency DC is going to be low impedance and high frequency AC is going to be high impedance. So it'll block AC signals. So similar to resistors, they sum in series and then they do the reciprocal sum in parallel. And the important equations to know for the inductor are that the voltage across it is equal to its inductance times the change in current across it. So you can basically, these are very useful, as we will see in, I don't talk about it yet, but in a couple slides. Does anybody have questions on inductors? Or like, I know magnetics can be kind of confusing. So is anybody confused on like how the coil works? I can draw one out. It's like you're drawing a coil, right? And then let's say it goes into the board. So this one's going into the board, and then it like comes around. And then this one's coming, or sorry, into the board, and this one's coming out of the board. And then it goes into the board. And then it comes out of the board. So if we use our right hand rule, this is a very quick and dirty explanation, but your right hand rule, if you put your thumb in the direction of current, then the rest of your fingers, when they curve, are going to show the direction of the magnetic field appearing around that wire. So let's say current's going into the inductor here. You put your thumb, current's going in. So the magnetic field is going to go around this wire that way. And then as we coil into the board, once, like imagine my hand's behind the board, now current's going that way and it's going up. And then we come back. So all the ones on the front are sending current or magnetic fields up, and all the ones on the back of the board are sending magnetic fields up. So you basically get a bunch of magnetic field. This marker's really bad. Here's one. You get a bunch of magnetic fields going through it like this. And so that's how you produce it. Like they're all going up, right? And there's a bunch of magnetic fields, right? And they're like, some of them go wide, some of them are really tight. And you just make this hole. And so that's how you're producing a magnetic field. And so then the reason they don't like to change in current is because this magnetic field is also producing a current, right? If you had a magnetic field going this way, it's going to induce a current in the wire that way. So it's like, that's what inductance is. Like it's going to try to put current back into these inductors. So we'll get into what that causes in a couple of slides, but that's an important thing to know, that it doesn't want the current inside of it to change. Just like capacitors don't want the voltage on them to change. So you can't change the current instantaneously in an inductor, and you can't change the voltage in a capacitor instantaneously. All right. So now getting into like how does this affect you, right? Basically the rest of this lecture is just a bunch of like different things that I thought was important. So if you have questions, like let's dive into any of these topics and spend more time on them. But resistance in circuits, an example is resistance in the high voltage path or any power rail. This is true for all power. Can cause brownout under high current load. So this circuit here is basically showing the part on the left is what a real voltage source looks like. There's going to be some resistance inside of that voltage source because it's real components, it's real metals, they have some resistance. So this is the simplest way to model a battery. You could also add some more RC components that are time dependent. So you could do like resistor, capacitor, as many of those as you wanted, and then it goes out. If you want to learn about RC modeling of a battery, I can talk about that at the end of this, but that basically creates some parts that are time dependent, but at the simplest, just a resistor, right? And as we just learned, current times resistance equals a voltage drop. So let's say that our battery is 600 volts, right? And let's say we got the resistance in our battery all the way down to like only 1 ohm. Like that's not a lot, right? Real batteries, it's like milliohms, but I'm making my math easy. Let's say it's only 1 ohm, right? Like you guys, that's not a lot, right? Like that seems pretty small. But it's a 600 volt battery. And now let's say the load is our inverter, which is going to be pulling some current across the resistance and have some voltage on the capacitance. Let's say our inverter is pulling 100 amps. Like that's a valid value for an inverter to be pulling. Now 100 amps times that R1 of 1 ohm is going to be a 100 volt drop. So now the voltage your inverter is seeing is only 500 volts. So it's much lower than what your battery is actually at. So you need to make sure that you either tell whatever is the load to pull less current, or you have something in the middle that can regulate that voltage so that it doesn't drop as much. But this is one of the downsides of like real power sources. So it's something to think about. In terms of cars, you would have something in the throttle controller to reduce the amount of throttle you're commanding in order to reduce the amount of current that you're pulling so that you don't brown out. Does anybody have any questions on that before I go to our next example? Okay. The next one I wanted to talk about like LEDs. How do they draw power, and how do you size like an LED driver? So I'm just drawing this as like a voltage source. So let's say we have some voltage source and we want to light up a light. We use this oftentimes, just put an LED on your power rail so that on your circuit board, you know if your power rail is active or not without having to probe it. You'll have to probe it to make sure it's like the right voltage and it doesn't have any ripple on it. But generally, you can be like, okay, something is on because I have an LED on it. So diodes, which we didn't talk about because I wanted to do more examples, but diodes will have a forward voltage drop. Like it's not just perfect across. So if we draw this out over, I'm just going to erase this. That means do not erase slow either. Okay, so we have voltage source, resistor, diode. Can everyone see that? Or- Sorry, I'm kind of blocking Liam with my laptop. So let's say our voltage source is 5 volts. And our LED, we look in it, and the data sheet says it's going to have a forward voltage drop of 1 volt. So basically, this voltage drop is going to be 1 volt, and this is 5 volts. So we know that our resistor is going to have to. Also, this is an example of like using a resistor as a voltage drop, like I said before. We know that this resistor is going to have a 4 volt drop, right? Because 5 minus 1. All right. So what resistance do we want this R1 to be in order to send the correct current through the diode? You can also think of it in the other way. How much current do we want to go through the diode? And then you look at the diode data sheet and you're like, okay, because the voltage drop changes a little bit. That's a bit more of a nuance, but what current do we want to go through here? So what you would do is you would go look in the data sheet at the graph for how much current, for how bright the LED needs to be. They have graphs for that. So let's say in this case, how do I make my math easy? It's like 4 milliamps. It's usually on the range of milliamps. If you find really good ones, you might get down to microamps, but milliamps is usually singular milliamps is usually good for a diode or an LED. Also, we're talking about LED, like light emitting diodes. This is not, when you use other diodes, there's a bunch of different types of diodes, which is why I didn't cover it in this one, but you'll slowly learn all of those as you start seeing them more. So we want 4 milliamps to go through here, and we know the voltage drop needs to be 4 volts, right? So then we just go back to Ohm's law. You put your voltage drop equals your resistance. And so 4 volts divided by 4 milliamps, it's going to give you a kilo ohm. And so we would put a 1 kilo ohm resistor here in order to get a 4 milliamp drop. And so now the question is, how much power does this draw? Does anybody know their equations for power, or like what equation could we use here for power drop? Because really, like everything on the car is getting powered off a battery, right? And if everybody's designing like 50-watt LED drivers, you're gonna have absolutely no space in your LV battery. Like that thing's gonna be massive. Also, 50 watts is a massively large number just for scale of reference. As you'll see when we calculate this right now. Anybody have any ideas for the power stuff? So equation, yeah. Yes. So one thing we could do is power is equal to V squared over R. So that is good for if you have a voltage across the resistor, you have voltage resistance, and that'll tell you how much power like this is dissipating. But those two values, like if you just did the 4 volts here, so that would tell us how much power this component's dissipating. But in this case, we want to know like the whole system.
Would it be equals I squared R?
Yes, so P is also equal to I squared R. And so that would give us the current, like if we use this current and the resistance, right? But if it's the current times the resistance, that's still just this component. Yes. So the last one is IV. Does anybody know how we got from this one to this one to this one?
Yeah,
How?
because V is equal to IR.
Exactly. Ohm's law. It's coming back already. It's already paying off. So yeah, right, if we go here, V is equal to IR, so we substitute IR into this, then you would get I squared R squared divided by R, so I squared R. And then if we separated this, you have I times IR, and IR is V, right? So now we have IV. So you can like substitute between all of them. So yeah, what I was getting at is if we use the current times the voltage, we can actually use 5 volts, right? Because we're dropping 5 volts across this whole thing. And then we know the current, which goes through all components. And so we have 5 volts times 4 milliamps, which is going to be 20 milliwatts. Yes. So this LED circuit is drawing 20 milliwatts from like our power source, right? So if we were driving like 5 different LEDs, now it's 100 milliwatts. And so this tells you the power, and then you can get the total energy consumed if you multiply it by time. So let's say we ran this 20 milliwatt LED for an hour, you could get a like energy consumed is like 20 milliwatt hours. Milliwatt hours is power times time. So it's like energy consumed. And so the LV battery that we have right now is 20 amp hours. They also measure in amp hours. But if you multiply amp hours by nominal voltage of the battery, you can get watts, right? Because amps times hours times volts. This is watts, yes, because of this one. So that's how you get watt hours. So if this was a 5-volt battery or something, then it would be, or wait, we already have this number. If you had a 5-volt battery, it'd be 4 milliamp hours, right? So you had 4 milliamps. And so if you were running like one of these, you would need a 4 milliamp hour battery to run it, right? So that's why low voltage budget is important, because the smaller the battery you have, the less it can weigh, the easier it is to package because it's not as large, a lot of things. So power is very important. All right, capacitance in circuits. Important things to know, inrush current is a thing that happens that you guys should know about. So when capacitance in circuits, like when you first turn on your board, the capacitances aren't charged at like time is equal to 0. So, right, if a capacitor is not charged, it looks like a short until you charge it up. So you're going to get this super big inrush current because you basically shorted power to ground. And so it's going to just be the voltage over whatever resistance is like naturally in your conductors. And so you're gonna overshoot on the inrush, and then you'll get down to like whatever current your board is actually just pulling to operate the components, because the capacitor is already charged. So if this is extremely bad, oftentimes you'll need like an inrush current limiter, which is basically what pre-charge is in a sense, is an inrush current limiter. But yeah, this is just an effect of like, how does capacitance manifest itself in your circuit board? The capacitors that you're using on your board will have inrush currents. And so why do we care about this? Because of decoupling capacitors. Decoupling capacitors are usually drawn like this in the schematic. You have the power on the top and the ground on the bottom. And then this on the bottom right is going to all the power pins of my microcontroller. So the reason that I have this is because the microcontroller, it's pulling power, and there's going to be, it's usually digital logic, so it's going to be like very jumpy. And so these capacitors allow, like you said before, how if there's a lot of changes in the voltage, the capacitor can kind of absorb some of that and source some of that. It goes back to basically the filters we were talking about before. You have some resistance in your circuit, then you have the capacitance. And so you're swinging one of the nodes a lot, and these capacitors will like source a little bit of current, absorb a little bit of current, source a little bit when the microcontroller is switching.
But in this case, we don't have the resistors, so how do we compare?
The resistor would be like from your voltage source resistance to your power pin, but typically that's like resistance or inductance. So it's easier to explain in the case of inductance, where let's say there's some inductance between your voltage source and your chip, which there will be like inherently. When you suddenly pull a lot more current than you were before, that's going to be like an instantaneous change in current. And so the inductor, like we said, doesn't like that. It won't be able to instantaneously source that current. It's going to take some time for it to be like build up that magnetic field energy. And so the voltage at your node is going to drop because you have a big dI/dt, and right, we said before, voltage is equal to inductance times the change in current. So if you have a big dI/dt times your inductance, you're going to have a voltage drop across it. And so instead of having your voltage drop on this power rail and your microcontroller browns out, you put these capacitors, and then the current will come from these capacitors to power your microcontroller until the rail has time to react. So that's what it means by like decoupling. It's decoupling your input power to the load. And so this is done with like microcontrollers. Every single IC that has power on your board should have like a decoupling cap on its power pin. Yeah, it's a very common thing on ICs and circuit boards. All right, number 2. This one's getting a bit more into the technical side of things. It's a bit more theoretical with some math behind it, but I'm going to try to explain it in just like a graphical way. So inside of your board, you're going to have all of your nets, right? So here's some examples of like PCBs. The yellow is the conductor and the green is going to be your insulator. And so capacitance, I guess I didn't go over this. Capacitance is equal to epsilon naught, which is like the permittivity of air, times the area overlap of the capacitor divided by the distance between the two, right? It's all right, up here, C is equal to epsilon naught area over distance, right? So as the area between two conductors gets bigger, the area they overlap, you're going to have more capacitance. As the distance between them shrinks, you're going to have more capacitance. As the distance increases, right, because it's in the denominator, capacitance decreases. As the area shrinks, there's less capacitance. So between the main point here, between every single net on your board and every single layer on your board, there's going to be some capacitor between those two, right? Because we've put two conductors and they have area and like distance between them. So there's going to be a capacitor between every net on your board. And so what is important about this? What I've written up here is a couple different ways that we like to route nets that need to be coupled to each other. And on the inverse, this also shows ways that if you didn't want two nets to be coupled together, you probably shouldn't do something like this. And so what does it mean for nets to be coupled together? Right, a capacitor, as frequency increases, capacitance reduces, or impedance reduces, right? So let's say on the differential microstrip, that's basically like I just have a pore on the bottom of my PCB, and I just have two nets running on top of the PCB, right? Let's say one of those was like a high frequency communication, and the other one was my power rail. As the high frequency communication goes like starts switching up and down, it's going to have a low impedance to my power rail, and now my power rail has like a bunch of switching on it, and that's not very good, right? Like that might affect everything that's on that power rail. So it's just something to keep in mind and think about when you're routing high speed. It should be far from your power, and your low speed should be far from all the high speed. When you do want two nets to be coupled, like can high and can low, right? We want those two to be seeing the same thing. We want them to always be next to each other. You would route them, you would use the differential pair tool in Altium. And so usually we use a differential microstrip. Microstrip and strip line basically means microstrips like on the top of the board. Strip line is if you had like a pour on the top of the board, then you put your signals in the middle, then you put a pour on the bottom of the board. And that's so that it's shielded on the top and the bottom instead of just the bottom. And then broadside is when they're on top of each other, coupled, and differential is when they're next to each other, right? So broadside is going to be more tightly coupled because you have bigger area, because the width of traces is larger than the thickness. All right, I know that was kind of a lot. Jared's falling asleep because no, I'm sure it's a tough day. It's a tough day. Probably didn't get great sleep last night. Make sure you guys go to bed early tonight, or not. It is Friday night. So does anybody have any questions on this? Hopefully, do people find this interesting or is this boring? Okay. Okay, that's good. Nikhil found it. He tried calling me, but I was busy lecturing. Oh, okay. Very nice. All right. Moving on. I think we're almost done. It is 4 o'clock, so I have to go to RFS. Yippee! Inductance in circuits. How does it like actually manifest? I know the other ones I all talked about like bad ways that it manifests. Well, I guess decoupling capacitors is a good way that it manifests. But here's another useful way. Using DC-DC switching regulators. A lot of you probably came across this in your recruitment projects. It's like, I have 12 volts. I want a 5-volt supply. How do I go between the two? Here's a couple terms for you to Google and research. You can have buck converters, boost converters, buck boost converters, choke converters. I'm just giving you terms to Google now because I don't have time to explain all of these. But at a high level, I'm just going to explain the buck so you understand what inductance is useful for in these types of converters. There's also many, many types of power converters. You don't need inductance, but in the on state, there's like a switch between the thing on the left is a voltage source and then the diode, right? So when the switch is on, you can send current through the inductance, right? And at first the inductance doesn't like that, right? But then the current starts rising through it. And then we can turn the switch off and right, the inductor doesn't like it when current stops going through it. So the current's going to keep going through it, but it's going to slowly discharge. And so if we switch between putting power through the inductor and not putting power through the inductor, we can actually get a fraction of the voltage that we put at the beginning. All right, I know there's a lot more that we can explain about how this works. I just wanted to give you a general, this is a thing that is possible, that you can divide voltage. And then the boost can multiply voltage if you rearrange the components in here. Mainly rotate the diode and swap the inductor and switch. But once again, inductance, how it manifests in bad ways. If you have really long wires, that wire is going to have some inductance and it's not going to want the current to change. That's just a characteristic of conductors. They have some inductance, and the longer it is, right, it sums in series. So longer wire, more resistance, more inductance, not great. Or smaller chip pins, like if you have a smaller radius conductor, the inductance is worse. So this is why when you guys are doing your ICs, usually they have multiple pins to carry power and ground because that's a high current signal. And so they have more of them because, right, inductors in parallel will divide based on the sum of the reciprocals. All right, any questions on this? Yeah.
I don't know if this is like a dumb question, but like, why can't we just use a resistor as like a
As your voltage divider? Yeah, I mean, no, that is a valid thing to do. You can divide the voltage. The main answer is efficiency. I can go through more examples of different types of voltage regulators. I think I had to cut that lecture out because we're doing other stuff this semester, but we can do like an extra session, just if people want to see that. But there's a whole bunch of different ways you could do it. Like you could also do, there's some diodes that have a reverse voltage blocking. So like what if we did a resistor and then we just reference the reverse voltage of that diode, or we can do switching regulators. It's basically an efficiency versus how much load current you're going to have trade off. So yeah, but that's a good question. That's an interview question. That yeah, which is why we should go into it more at a later time. All right, last slide on inductance. Important thing to note: inductive voltage spikes. Right, so I said inductors don't like it when the current through them changes, and it can't change instantaneously. But if you had a circuit component that basically cut off the voltage in the inductor, or I mean, cut off the current through the inductor, like a switch, and it opened up, and there's nowhere for that current to go, the inductor is just going to drive that voltage as low or as high as it needs to allow the current to go through it. So basically, you could have a pulse like this, where on the bottom you see we have the inductor current starts charging up, and then if we suddenly cut off that current with like a switch or something, the voltage, it's just going to go as low as it wants. Like the inductor will decide what it wants and it'll do it. So it's really up to us to like try to make the inductor happy and solve that. Like you're not going to stop the inductor from doing this, but you can clamp it and send the energy elsewhere. How to solve that is not necessarily in the scope for this lecture, but I just want you to be aware of this because you might be probing something on the car or on your board and you're like, oh no, there's a massive spike when I like do something. It's like, okay, maybe I should start looking for inductance somewhere in my circuit or PCB. And a lot of times this voltage spike can exceed the max voltage rating of whatever is on that net and break the device. So it's important to like take care of this. All right, last slide. Yes, last slide. How does this apply to my design? I've sort of been saying how this applies to you throughout the lecture, but this is just a couple things I wanted to add before you guys get too far into your boards. Trace width. How wide does your trace need to be so that you can reduce the resistance so you don't have these brownout concerns on your power? You can use this DigiKey trace width calculator. You basically put in the current going through the trace, how thick it is, which is usually like, we usually use like 1 ounce copper or half ounce for inner layers. And then what the ambient temperature is, how long the trace is, and then what the allowable temperature rise is. We don't have an exact value for that. Usually I put in like your ambient is 25, although it's a little high. And then I'm like, it's fine for it to go up to like 60 because that's like how high the accumulator temperature can get. So it's like sort of a good rule of thumb reference. It's not an exact numbers. If you want more exact numbers, you have to figure out what your actual allowable temperature rises, like what's your application. And then this will tell you basically, you can fill out any of these boxes and then leave one of them empty. And when you hit calculate, it'll figure out that one from the 4 you filled in. So usually I put in everything except for thickness, and then it tells me how thick it needs to be. And then the other option is polygon pores. These provide solid copper across your entire board. So for best signal integrity, like we were talking about earlier, and what I want everybody to do on their boards is use a 4-layer PCB and make layer 2 and layer 3 solid ground pores. And this basically shields your top layer, layer 1, and your bottom layer, layer 4, from each other. This lecture didn't exactly go into how shielding works and how differential pairs work, but it basically stops, like, remember how we talked about the capacitors between the 2 nets? Imagine now if you just had a sheet of ground in between. Instead of the capacitor going from like the bottom layer to the one above it, if you had 2 signals running over each other, it's now like a capacitor to ground and then a capacitor from ground to the other signal. So instead of having capacitors between the top and bottom signals, you now have capacitors to ground on both sides, which is better. You also put ground pores on layer 1 and layer 4, but it's okay for them to get cut up because your signals need to go somewhere, right? Just make sure you use via stitching across your entire board on the grounds layer. And if you need help setting this up, I can help you, or I think it's also in the PCB handbook. It's also like 2 buttons, so if you Google it, it comes up. But you basically do this. Via stitching is like across your entire PCB, you put a bunch of vias everywhere in like a grid, and it basically it's like sewing the board together. It shorts all of your ground layers together so that instead of having like layer 3 is ground, layer 2 is ground, and I have one connection point, then you could have resistance between one corner of the board and the other corner of the board, right? So your ground planes could actually be different voltages. This basically ties them together much better. Which once again goes back to like resistors, right? It's basically like having a bunch of them in parallel, so it's much lower resistance path. Oh, last one. Differential pairs. I just want to make sure that everybody knows that there is a differential routing tool in Altium, and to make sure to use this tool when you route your CAN traces or any other differential traces. You basically right-click the normal routing tool, and then you just click the differential routing tool. And it requires that you defined them as differential pairs in your schematic, which, once again, when you have to define the CAN traces, we'll explain that. But everybody on the team should know how to do that. This is like new knowledge we've been spreading without the team. Any questions before we wrap up? Yeah.
Of multiple ground layers separated by the top and bottom layer shield with the layers.
Yeah, so basically shielding is the idea that you have a large conductor typically connected to ground surrounding or next to or like between two signals you want to stop from interacting with each other. And the reason that that works is it's easier to draw with like a coaxial cable. So you'll cover this in 7B as well, but you have like an outer cylinder conductor, like this is a tube going through the whole board. And then let's say there was some electric field outside. All of these electric field lines are going to go like this. Because electric fields go from higher voltage to lower voltage. So they'll just go to your outer conductor, and then the charge contained within an object that's shielded is like, that's like your internal conductor. Like it will basically shield it from any electrical field interference. Yeah, I need to review this a bit more to explain it more clearly, but it's basically the charge inside of a conductor is protected from the environment. Or is that the best way to state it? But yeah, and the other thing I'll just go through real quickly right now because we're talking about it is differential pairs and twisted pairs. So CAN is like a twisted pair and isospy is a twisted pair. So it's basically like you have one conductor and it's going like this. And then we have the other conductor and it gets like routed around the other one. So it's like two conductors and they get routed around each other, twisted pair. This is how you protect against magnetic field interference. So, right, we have the conductor going through one of them and the magnetic field will go around this way. And then the idea is that you have the magnetic field returning through the other one and it goes the opposite way. So that it's like a current loop so that the magnetic fields cancel out. So it stops them from like mutually inducting each other, but it also, if there's any external fields that are like coming and hitting it, they're twisted around so they see like the same thing at all times. So it's usually differential signals so that you're a common mode. You have as much common mode and not differential mode noise. Yeah. All right. Time to go to RFS.